Right, we've got an emergency lighting system. They tell me that the EMF is 12 volts, so that's an EMF value. There's 2 floodlights. They tell me that they each 0,5 ohms. There's a pilot light of 24 ohms. The internal resistance is 0,1 ohm. And let's see what happens. What will the reading on the voltmeter be when the switch is open? When the switch is open, there's no current flowing, and therefore the reading is going to be the EMF. Briefly explain why the reading on the voltmeter will drop once that switch is closed. You need to say that when current is flowing, it uses some voltage or some of the potential difference to move charge through battery. Because of internal resistance. And those are your lost volts. That decreases the potential difference when we close the switch. Calculate the total effective resistance of just the external circuit. So it's 1 over R parallel is equal to 1 over 24 plus 1 over 3. You find a lowest common denominator and you land up with 9 over 24. Then you need to say R parallel, don't forget to flip it, is 24 over 9, which is equal to 2,67 ohms. That's the entire external circuit. What is the current flowing through the battery when the switch is closed? Now that means I'm looking for a series current over here. And in order to do that, I don't have an external potential difference, but I do have internal resistance. So I can now work out the total resistance. And the total resistance is going to be 2,67, which is the external, plus the internal 0,1, which is going to be 2,77 ohms. Now I'm able to say that the current is equal to the EMF divided by the total resistance of the entire circuit, and that is going to be 12 divided by 2,77, and that turns out to be equal to 4,24 amps. Once I know that, they want to know what the reading on the voltmeter is. So now we want to know about this voltmeter. This is an external voltmeter. It's reading what is going on, what energy is being used by the external circuit. So I can say V is equal to I times R. What current? The series current, which we happen to know is 4,24. The resistance of the external circuit, which is 2,67, and I land up with a reading of 11,57 volts. Now it says calculate the power dissipated by the power light when the switch is closed. So we're only interested in that power light, in that pilot light. We've got the potential difference. There it is. It's the same between pale pink and pale blue, pale pink and pale blue. So we've got the potential difference across there, and we've got the resistance. So we can use the equation power is equal to V squared over R, and that is going to be equal to 11,57 squared divided by the resistance of just that resistor, which is 24, and I land up with 5,57 watts. Then it just goes on to say, if the filament in one of the floodlights were to burn out, what would happen? So firstly, if one of them burns out, that entire branch disappears, which means that the resistance of the whole circuit increases, but this pilot light over here lands up getting a little bit more current. Why? Because it doesn't have to share it anymore with that branch over there. So the brightness of the power light does increase. And then what happens to the reading on the voltmeter? Turns out it also increases. But let me show you why. We've now got to work out the new current because the current's just changed. So I'm going to say my current is equal to my EMF, because the EMF doesn't change, divided by the new total resistance. EMF is 12, and my total resistance is now 24,01. Sorry, not 01, 24,1, because I've had to add the internal resistance. What have I got? I've got the internal resistance, and I've got this one little external resistor over here. So when I do that, I land up getting 0,0 0.497. Keep that whole thing in your calculator, okay? That is my new current. I'm interested in this new voltmeter reading. V external is equal to my series current, which I've just worked out, multiplied by only the external resistance. So it's going to be 0.497 multiplied by 24, and I land up with 11.95 volts. And as you can see, 11.95 is higher than 11.57, so it did increase. If I take a look at this circuit over here, state Ohm's law, you expect to be able to state all of your laws without even blinking and getting your 3 marks in the bag. It says that provided the temperature remains constant, for a certain resistor, the potential difference is going to be directly proportional to the current strength. You've got to say that you've got a fixed resistor, you've got to say that you have got a constant temperature, and then describe the proportionality of V being directly proportional to I. And you've got to use words when they say state. You can't just use the formulas. What is the ammeter reading in this particular circumstance? So the first thing I'm going to do is I'm going to work out all of the resistance of the circuit. So 1 over R parallel is equal to 1 over 40 plus 1 over 60. That lands up being equal to 5 over 120. R parallel turns out to be 120 divided by 5, which is equal to 24 ohms. Then I have got the total resistance of the circuit is equal to 24 plus the 25,5 in series, plus don't forget the internal resistance of 0,5, and I land up with 50 ohms. So if I'm looking for the ammeter reading, I is equal to the EMF divided by the total resistance if I'm using EMF. So it's going to be 12 divided by 50, and that turns out to be 0,24 amps. What about the voltmeter reading? The voltmeter is across the external circuit, so I am going to say that the voltmeter for the external is equal to the series current multiplied by the external resistance. So that is 0,24, and that's multiplied by only the external, which is just those two over there, which is 49,5, and that lands up being 11,88 volts. What about the current just in the 60 ohm resistor? This is where things get tricky, and you can use ratios if you're good at ratios, but ratios are tricky. So I'm going to just connect an imaginary voltmeter over here, which remember that that voltmeter will be the same as the voltmeter reading across the 60 ohm or the 40 ohm resistor. If I were doing this using colors, I would have had the following. It would be, let's say, between blue and say pink, and as you can see, I land up with the same voltmeter reading regardless. Alright, let's calculate this voltmeter across here, and the voltmeter for the parallel network is equal to the resistance of the parallel network multiplied by the series current, because all of the current ultimately does go through there. So the resistance of the parallel network is 24 multiplied by the series current, and the series current we worked out a little bit earlier to be 0,24, and therefore we land up with an answer of 5,76 volts. Now that I know the voltmeter reading across the 60 ohm resistor, I am in a position to say that the current going through the 60 ohm resistor is equal to the potential difference across the 60 ohm resistor divided by the resistance of the 60 ohm resistor. So the potential difference is 5,76 divided by 60, and I land up with an answer of 0,096 amps. There is another way of doing it, and that is to have said that I'm going to take the series current of 0,24 divided by 100 and multiplied by 40, and you land up with exactly the same answer. What is the energy dissipated in this series resistor after 5 minutes? I don't have the potential difference, and I don't have the current, but I have calculated the current. It's over here. So I'm just going to use that current reading over there, but there were different ways of getting this answer. This is just, in my opinion, the most efficient. it's I squared RT 0,24 squared. The resistance 25,5, and you have to multiply that by time, and they said to you it was 5 minutes, which is 5 times 60 seconds, and you land up with an answer of 440,64 joules. And finally, how would the reading on the voltmeter change if the switch was opened? Well, now suddenly that disappears, so we've landed up with more resistance in this circuit. So the total resistance increases, and therefore the external circuit requires more energy per unit charge, more potential difference, and therefore V is going to increase. Right, we have the Haber process. We've got quite a lot of information over here. We've got the chloralkali process that makes the hydrogen. You don't have to worry about that. We're going to do it later, but you don't need to know about it yet. They give you all these balanced equations. They tell you what's exothermic and what's endothermic, and then there are some questions. In terms of reaction energy, what type of forward reaction is represented by the Haber process? That is delta H is greater than 0, so that is an exothermic reaction. State Le Chatelier's principle. You have to be able to do this. It's 3 marks. It's not difficult. You need to start by saying if a system is at equilibrium and then disturbed by a stress, the system will shift the equilibrium in order to minimize that stress. When considering the effect of each of the following changes, answer only increase, decrease, or no effect. What effect does the use of an ion catalyst have on yield? Yield is not affected by catalysts, so there's no effect. The next one, what effect does increasing the temperature have on the yield of NO in the first step? Now, over here we've got an exothermic reaction, and therefore, if I increase the temperature, it's going to favor the reverse reaction, and as a result, what's going to happen to the yield of NO? That will decrease. What effect does increasing the pressure have on the solubility of NO2 in the last step? Now over here, I'm putting NO2 into water. I've got 3 gas moles on the left, and I have got of gas, and I have got 1 gas mole on the right. So if I increase the pressure, I'm going to favor the side with the least gas moles. So I'm actually going to increase the forward reaction, which is an increase in dissolving in the water. So it is an increase. And finally, what effect does reducing the volume of the vessel have on the rate of the oxidation of NH3? And that reaction, oxidation of NH3, oxygen plus NH3 in the Ostwald process, I have to reduce the volume. Let's see how many gas moles I've got. I've got 9 gas moles on the left, and I've got 10 gas moles on the right. So if I reduce the volume, what am I doing? I am increasing pressure. And they're asking about rate, so I don't even have to think about how many gas moles actually. All that happens is if I increase pressure, I will increase the rate of any reaction. It really doesn't matter. I've now got a certain number of moles of COCl2, and we put it into a syringe, and we adjust it, and we make some CO and Cl2. So to start with, I had no CO and Cl2, I had lots of COCl2. I'm going to use the equation in the graph to answer the questions. How much time was required for the system to reach chemical equilibrium? If I'm looking at number of moles, chemical equilibrium is reached when the number of moles stabilizes, so that took 30 seconds. How do the rates of the forward and reverse reactions compare at T75? At T75, I am getting less and less of these two, they're going down, while simultaneously the COCl2 is going up. That means I'm favoring the reverse reaction. So how do the rates compare? The reverse is greater than the forward. How do the rates of the forward and the reverse reactions compare at time 105? So I go to 105 over there, and as you can see, everything's stable, which means that reverse is equal to forward, because it's the same number of moles. Use Le Chatelier's principle to explain why the number of moles of each substance in the mixture changes between T45 and T105. So let's first try and get ourselves into the right place over there. It's T45 and T105. So this is where we're interested. What in heaven's name happened? Well, firstly, there was a big fat spike over here, which means I must have added some Cl2. Cl2 is product. Therefore, the reverse reaction, the system tries to compensate, and the reverse reaction is favored. That means if the reverse reaction was favored, I made more CoCl2. That seems to make sense. I've made more CoCl2. There it is. And I have got less CO and less Cl2. Let's see. Yes, as it turns out, that goes down and that goes down. So all of that has been explained.